Welcome. Today we're going to take a look at exponential and logarithmic functions in terms of their graphs. Really I think the best thing to think about today is to remember that the logarithmic function is the inverse of the exponential, and when we're graphing them, those are the things that we should be thinking about. For example, if I want to graph the function log base 2 of x, it will be to my extreme advantage to know what the function 2 to the x power looks like, because I know with inverses you switch x and y. So as I approach this problem, I'm going to do exactly that. I'm going to look at the exponential function, and I have a pretty good idea what that looks like. But then once I know what it is, I can graph the inverse by switching x and y. So I have a selection of x values to put in, and 2 raised to the negative second power, you'll recall, means that we're really talking about 1 over 2 squared, or 1/4. 2 to the negative first power, 1/2. 2 to the 0th power, well, anything to the 0 power is 1. 2 to the first we're all familiar with. 2 squared is 4, and 2 cubed is 8. Now I'm going to go ahead and graph that. When x is negative 2, so here, y is 1/4, very just a little bit over the x-axis. When x is negative 1, we go up to 1/2. So that's about a quarter of the way through the square. The scale is 2. When x is 0, the value of 2 to the 0 is 1. When x is 1, when x is 1, the value of 2 to the first is 2. When x is 2, 2 squared is 4, and you can see that exponential curve is starting to take shape. When x is 3, we're up to 8, and by the time x is 4, we're off of my scale. So here's the exponential function y equals 2 to the x, and you see it has the asymptote here at y equals 0. My claim is that to graph the logarithmic function, we need the inverse of that, and so I would choose my x values now to be these y's. When x is 1/4, that means that the log base 2 of that x is negative 2, just switching x and y. When x is 1/2, y will be negative 1, etc. I'll go ahead and write those down here real quickly. Log base 2 of 4 is 2. That's the exponent you need to raise excuse me, 2 to get 4. And when x is 8, the log is 3. So I'm going to go ahead and change colors because I often do that when I'm graphing, and let's take a look at what this looks like. Alright, when x is 1/4, so really close in here, the y will be negative 2. When x is 1/2, the y will be negative 1. At x of 1, y is 0. At x of 2, y is 1. At x of 4, y is 2. And finally, at x of 8, y is 3. So here comes our inverse function. And hopefully I get a little good curve there. You'll see that the tail of it hugs to the x-axis, so it has a vertical asymptote at x equals 0. This one had the horizontal asymptote at y equals 0, and you can see very clearly from our picture that these two are inverses. Indeed, an inverse switches x and y, or it's a reflection over the y equals x line, and we've done a pretty good job of showing that. As long as we're talking about logarithmic functions today, we would be remiss if we didn't talk about domain and range. And you can see that for the logarithmic function in its generic, the domain of the logarithmic function then has to be x bigger than 0, because you notice it has the asymptote there, so x has to be bigger than 0, but it can go toward infinity. And notice we have curved parentheses on either end to say that 0 is not part of that domain. The range in interval notation, well, y can be extremely small. Any y is okay. And as you can see, this goes on forever and ever. So the range is from negative to positive infinity for a logarithmic function, a generic one. As far as x and y intercepts, there is no y-intercept for a logarithmic function in its generic form. It never touches the y-axis. However, it does have an x-intercept, and if nothing has been done to modify the rule, the x-intercept will be 1, or the point 1, 0. The value of b obviously has a lot to do with the shape of the logarithmic graph. If b is greater than 1, that denotes that you're an increasing curve. And in fact, our example was b of 2, and you can see that that is an increasing function. If the value of b is between 0 and 1, that would be a decrease, or our curve would be decreasing. Okay. As far as asymptotes, with nothing having been done to modify the function rule, the logarithmic function has a vertical asymptote at x equals 0. Yeah, so it has a line of avoidance there at x equals 0. Very good. Let's see if we can apply that a little bit. Our next screen is going to ask us to graph f of x 1/2 to the xth power and its inverse, which would be the log base 1/2 of x. We're going to proceed. We'll build a table of x and y values for first the exponential 1/2 to the x. We'll find the inverse of that function by switching x and y and coming up with the graph of log base 1/2 of x. So let's start here. As I often do, I'm going to start my x's in the negative territory, and since I know a little bit about this one, I'll be starting with x values that range from -3 to 2. And as I put that in there, 1/2 to the -3rd power, folks, is like 2 to the 3rd power. Just remembering your exponent rules, that would give us a value of 8. 1/2 to the -2nd, it's the reciprocal, 2 squared, or 4. 1/2 to the -1 would be 2 to the 1st, that's the reciprocal, or just 2. Anything to the 0th power, so 1/2 to the 0th power is 1, 1/2 to the 1st power, and 1/2 to the 2nd power would be 1/4. So there is our exponential function. So as you look at this one, and I'll graph it as well, when x is -3, we're up here at 8. When x is -2, we're at 4. When x is -1, we are at 2. When x is 0, y is 1, and that's what you would expect for an exponential. We have that y-intercept of 1. At an x of 1, y is 1/2. And as x grows, that gets shorter and shorter. It shrinks down there toward the x-axis. It can't ever quite hit it, but it tries. Well, I did not do a very good job of getting that curve in. There's our exponential equation. Let's change color and look at the logarithmic one, which would be the invert, or switching x with y. There we go. Do the switch, and let's plot those points as well so that we can get a picture of this. Notice that this exponential is decreasing since it has that b value that is between 0 and 1. When x is 8, y is -3, so down here. When x is 4, y is -2, so right there. At 2, we're at -1. At 1, we're at 0. So this time we get an x-intercept. When x is 1/2, so in here we're up at 1. That's going to cross over right there. When x is 1/4, we're up at 2. So very close in here. And again, this function is going to hug along. This time the x-axis, or the y-axis, it has to do the opposite of the behavior of its inverse. And so we have that reflection over the y equals x line. So These logarithmic functions are no different from any other functions. They can be transformed in the same way. So now we're going to give you a little memory test here. Suppose we took our logarithmic function above here and we changed it this way. We put a negative in front of it. Inside, we put a +2, and outside we have a +3. Can you remember what transformations we've made to that function? What's that negative in front do? The negative, ... reflects it over the x-axis, since it's on the outside, not inside the function rule, but on the outside. That's a reflection over x. The 2 that's inside here with the function rule, that's a shift. And in this case, we're going to shift, let's see, 2 units left, because remember it goes the opposite of what you'd expect in there. It says +2, but it really is moving in the negative direction. And then it's going to also shift 3 up. So the same transformation rules that we've learned before apply to logarithmic functions. They are just functions, you know, so they have to be saved the same way. A vertical shift, this one would go up C units, this one would go down C units. When the shift factor, the plus or minus, is inside the function rule, left here, right there. And this one reflects over x. When that negative is inside the function rule, that's a reflection over y. The vertical stretch and shrink, we called those expansions and compressions before. It depends on the size of C, and you'll remember that when C is greater than 1, that's a vertical stretch. It's growing, so I'll put vert stretch or increase. It becomes more vertical, or some people would say closer to the y-axis, so I'll add that as well, closer to the y-axis. When C is between 0 and 1, the opposite happens. That's a shrink in the vertical direction, a vertical shrink or compression, and that means it gets less vertical. It moves farther from the y-axis. Horizontal shrink happens when the multiplier is inside with the function rule, and it behaves exactly the opposite of vertical. So when C is greater than 1, we get a horizontal shrink. That is, it gets less horizontal, and it moves away from the x-axis. When that shrink factor, or that multiplier, sorry, is between 0 and 1, this time we grow horizontally, so it's a horizontal stretch. That is, it gets more horizontal, or it moves closer to the x-axis. All right, very good. And you'll remember those rules from before, so that's just a little trip down memory lane. We want to take just a moment to talk about the domain and range of logarithmic functions. You'll remember that when we worked with inverse functions before, that things get switched, x with y. That means domains and ranges get switched as well. So the domain of the original function is equal to the range of its inverse, and the range of the original function is equal to the domain of the inverse. So you think about that with logarithms then. For logarithmic functions, their domain is, well, it's the range of an exponential. And exponentials, unless they've been doctored, have ranges that are greater than 0. Their range becomes the domain of the exponential function, and that means that since any number can go into an exponential, any number can come out of a logarithmic function. In general, the domain of the log base b equal to g of x consists of x that makes a positive g of x. So it's x such that g of x is positive, bigger than 0. Alright, let's take a look and see if we can't apply that here. This asks us to find the domain of f of x equals log base 4 of x minus 5. Well, the rule says we got to have x's that will make this part be bigger than 0. So we need x's that will make x minus 5 bigger than 0. Well, you think about that. If we want this to be bigger than 0, it cannot be 5 because 5 would make it 0. Instead, it has to be greater than 5. We can show that in interval notation by saying 5 is not included, but then it can go on from there. Okay? Any number 5 or larger is okay. If you were writing that in set builder notation, you'd say that it's all x such that x is greater than 5. Okay. Here, similar thing. This would be a good time to pause the video. Figure this one out for yourself. We want the domain of f of x, if that is the natural log of quantity x plus 2. What cannot happen? This cannot be 0 or less. It has to be positive. So negative 2 is not okay. But any number larger than that is okay. Negative 2 would make this 0, but as soon as we get to, say, something bigger than negative 2, like negative 1.5, this becomes positive, and that's all right. In set builder notation, which I happen to like better, as you know, that would be all x such that x is greater than negative 2. And that's the domain rules for logarithmic functions in general. Alright, that's the end of our lesson today. We're going to ask you to get out there and try that U-try as quickly as you can. Remember, it is due before school starts tomorrow. Hope you have a great time, and we will talk with you tomorrow.